Hi, my name is Amy Sullivan, and I'm the current immediate past president of AAAR. And it's my pleasure to welcome you to the 42nd in our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So with these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us a chance to come together outside of the annual conference. So each month, the editors of AS&T select a high-impact paper to be presented by its authors. Each of these lectures are being recorded and will be posted later to our YouTube channel, which you can access from the AAAR website under the Events tab. In addition, each of these lectures is being recorded as well as being hosted by one of our student chapters. And so I want to thank all of you for joining us and everyone who's helped to make these happen. And with that, I'll turn it over to our student chapter host from the University of California, Riverside. Thanks.
Thank you very much. Hello, everybody. Good morning, good afternoon, good evening, wherever you are. My name is Erin Bowie. I'm from the UC Riverside AAAR student chapter, and today's AS&T lecture will be presented by Dr. Lydia Morawska, and it's such an honor for us to get to introduce her. So Dr. Morawska received her doctorate in physics in 1982. We were just clarifying the year before this meeting at the Jagiellonian University in Krakow, Poland, for her research on radon and its progeny in the air. And she then became a research fellow at the Institute of Physics and Nuclear Techniques, also in Krakow. And after this, she traveled to Canada to complete postdoctoral research with the International Atomic Energy Agency at McMaster University in Hamilton, and then at the University of Toronto. And currently, she is a distinguished professor at Queensland University of Technology in Brisbane, Australia, and has lectured and researched there for over 3 decades. During her prolific scientific career, she has also received so many awards and accomplished so many incredible things. So I'm just going to name a few. So at QUT, she has established and directs the International Laboratory for Air Quality and Health, ILAQH, a World Health Organization collaborating center for air quality and health. And she's a longstanding collaborator and advisor to the WHO and has contributed to essentially all of their air quality related guidelines since 1990. And has also helped to develop numerous related standards. She has also received the Prime Minister Prize for Science in 2025 and was included in Time's 2021 list of the 100 most influential people in the world for innovation. And there's so much more, but I hope that that communicates how important her work has been. Her research has a specific focus on the science of airborne particulate matter. It looks into questions on pollution and disease transmission through air particles. Many of you may know of her work on SARS-CoV-2, showing that it travels primarily through the air. Also on vegetation fire and resulting haze events, and indoor air quality in modern conditions, and the need for low-cost sensors, all of which is extremely relevant. Dr. Morawska is an author of over 1,000 articles and chapters. I see many sources note just that sheer number, but the impact of each one of these works is also incredibly impressive. They collectively build a clear and direct argument that everyone deserves to breathe safe and clean air, and what we should do to get there. The focus of her lecture today will be on low-cost sensor responses to bushfire and haze. We get a lot of wildfires in SoCal, and there are lots of low-cost sensors here. And it's through work like Dr. Morawska's we can better advocate for why things like this are so important. So now as we listen, please feel free to send questions in the chat, and we'll do Q&A after, and I'll let Dr. Morawska take over to present the lecture. Thank you.
Many thanks, Erin, for your introduction, and many thanks for inviting me to give this lecture. Well, let's start first with sharing my slides to make sure that it works. Okay, let me know, please. Can you see it well?
Yes.
Yes, all right. Well, that's the title of my presentation. That's what I was invited to talk about. And this is based on a paper, Responsive Low-Cost Sensors to High PM2.5 concentration during bushfire and haze events. This is a very interesting paper. The paper which was championed by that stage former PhD students, Xiaoting Hu and Budi Pushpavela. They both, by that stage, graduated. Xiaoting's PhD was focused, in fact, entirely on low-cost sensors and applications to all kinds of situations and environments. Budi's PhD was more on particles and ionization processes on particles and for what follows. And when the two young ladies finished their PhDs, they realized that there was still so much data left from the investigations they were involved with. So they decided, let's put it together and let's present another aspect of this, which is that bushfires and haze events on a bigger background of the longer term measurements in those two locations. So there's lots to talk about. And if I were to talk just about this paper, I guess everybody would probably be lost in details because there are lots of interesting details. So what I thought I was going to do, I will talk in a broader picture that work in the context of a broader picture, which is low-cost sensors, big picture, koala, what animal is this? Low-cost sensors, that's calibration and data interpretation, the specific focus on bushfires and haze, and then future applications of low-cost sensors. Well, I start perhaps with something which everybody would expect at the end, which is the bottom line. But I guess without understanding this, the picture would be more difficult to capture. Some say that low-cost sensors lack precision and accuracy, but this displayed the lack of understanding of the physics of low-cost sensors operation. That's what I always say. We cannot expect that optical measurement instrument give precise gravimetric mass, because that precision is always referred to gravimetric mass. Another aspect is, unless liquid particles, which is Fox, are dried, they will be counted as particles. That's what that drying happens in regulatory instruments. So, but if particle optical properties are accounted for and moisture dried, precision and accuracy can be achieved. So this little things, low-cost sensors, are incredible tool if you know how to use them and for what you want to achieve. And what I stress, this is not just pressing the on button, what many things it is, because it is as easy as this. So basically, this is the bottom line, and that's almost a conclusion, which I hope you'll see is at the end of my lecture. So this big picture. Paradigm shift. So it was some time ago, 10 years ago, more than 10 years ago, when the low-cost sensors started kind of appearing in our publications, in our scientific conversations. So the change of paradigm of air pollution monitoring, that was 2013, and a little bit later in 2016, that paper in Science of the Total Environment with colleagues, where we specifically focus on application of them in indoor environment. What we concluded in relation to indoor environment, it is not the technology, the sensors, it is just that there's lack of appreciation and importance of indoor environment. That was a few years before the pandemic when this came in the full view. So those things were kind of appearing more and more. But for me personally and for our team, it wasn't until that moment when we received this grant, Australian Research Council linkage project grant on developing and utilizing advanced network of air quality sensing. That was the aim of the grant. Now, well, okay, we applied for the grant, we got it, but maybe a few words about the history, why I decided to apply for this grant. This was because the situation in funding was actually getting worse and worse in Australia, and particularly funding on anything to do with environmental research like air. So in a frustration, one year that we didn't receive a grant or grants we applied for, and I was like, what are we going to do? I looked at the list of successful grants, and it was technology data, technology data. So I thought, okay, we've got to be smart, and how are we going to, well, to outsmart it? And I said, okay, those sensors are coming, there's technology, we apply for a grant, well, maybe we'll have a chance. And yes, we got the grant. But even then, I wasn't fully really interested in this. I thought, well, we are using all this state-of-the-art instrumentation, specifically for particle measurements. What are we going to learn from these low-cost sensors? How wrong I was then, and how lucky it was that we did this. This is really one of the most important moments in our center to get into that area at the right time. So a few words, what constitutes the change of the paradigm? Flexibility in deployment of the monitoring networks, the use of data, many different ways and applications. I'll just mention a few of them, but there are many more. And there are options, large networks, advanced numerical methods, machine learning that's coming more and more, particularly with AI. Small networks, methods adequate to solve the problem, sometimes a very small local problem, which can be solved with this network applied right here, right now. What do we expect from low-cost sensors? Well, all of this. They should be low cost, reasonably accurate, not drifting with time, long-lasting, robust, small, quiet, needs little power, transmitting data to our database. And we have an image of this low-cost sensor like a button, like something very small. That's the sensor, and that's what the sensor is. But by the time we achieve all these objectives, or some of them, depending which are the most important, we really created a system, which means a monitor. So really, when we are talking about applications and doing anything, we are not talking just about the sensor. We are talking about monitor, and dependently what that monitor is purpose for, some of the things are more important, others less, or some are better, some are worse. So this is very, very important to understand that it is not just a tiny little thing which is a sensor. And I'm sure, well, many of the listeners have already experienced with low-cost sensors, so you know those things. But it's not that everyone who starts using or wants to use those sensors knows about this. So it's important to remind them. So from sensors to the outcomes of the application. So as we were well gearing up to develop the low-cost monitor, decide which sensors to use, and so on, we reviewed what existed. We reviewed lots of things, and that was the paper which was then published about the application of this technologies and how far have they gone. So then we presented this kind of framework, what it involves. So sensor is the beginning of the process. Then there's monitor. In this, we have the selection, assessment, laboratory field, then the deployment and all kinds of ways we can deploy these sensors. And then data, viewing, harvesting, storing, analyzing, and outcomes, what outcomes in relation to the aim. So this picture is getting much bigger, not just that little box of a sensor or a monitor as we imagine. So the sensor is just the beginning. So now this brings me to koala. Koala, what animal is this? Is this animal here? We don't see them very often here at least in Brisbane in the wild sometimes, but it is not. It is this koala. And I'll come back to why this monitor is called koala in a minute. So the first question when we decided to, well, we got a grant to build a monitor was which pollutants to measure, which sensors to choose. And as we reviewed the sensors available then, they were basically for a whole range of gaseous pollutants, all these ones here on the list. Also for measuring compositions, chemical composition, for particulate matter mass, as they were named, but we've quickly found that it's not gravimetric mass. So we then found out then, that was 2018 or something like this, that the most advanced were CO and particulate matter sensors, and also in terms of data interpretability. Some of these sensors, other gaseous sensors, were also advanced and are advanced and very useful. However, interpreting data is sometimes more difficult, like, for example, NO, because of interference with other pollutants, for example, ozone. So that's why our focus was on these two sensors. So our considerations were pollutants most related to health, because that's in generally focus of our work. So the choice was PM2.5 and CO. Pollutants for which low-cost sensors not only exist, but what are reliable. Not too many of them, because first of all, why to put sensors of which data we were not going to use? But this would require power, and we preferred a small battery to power them such that they could operate longer or in a better way. So that's why just two. And still, we wanted to get some idea about the sources. And the point is that PM2.5 are generally larger particles, larger in terms of if we compare them with ultrafine particles. So they are at the tail of dust, which are much larger particles, or aged smoke, and CO is combustion. So between these two pollutants, we were able to tell quite a lot about the source or source mix. So that reminder about how those low-cost PM2.5 sensors operate. As I said in one of the first point in my bottom line, they are optical sensors, basically all of them. Light scattering will work in principle of all these mass low-cost sensors. I put this in quotation mark because they really measure particle number. We, as I mentioned, at the beginning, we reviewed and tested, I think it was 6 different types of sensors, and that was sensors, not monitors. We put them in a chamber and subjected to many different types of aerosols, so it was sharp, shiny. But at the end, we focus on plant tower, and that was the choice. And then once we've chosen this, then from this was the building of a monitor with the housing protected against elements, and not only elements. One of the biggest problems we faced were creepy and crawling. Spiders, for example, and other types of things which could crawl into the monitor and then transmitting the data. So this is the koala monitor. This plant tower particular model, which claims that, well, which claims that they measured a report PM1, PM2.5, PM10, but they really measure particle number concentrations in 6 channels, and starting from about 0.3 upwards. And this was alpha sense for carbon monoxide. Also temperature and relative humidity, but the point was that this was more for diagnostic purposes, because since the sensors are inside the instrument, they don't reflect the outdoor temperature. After testing over the years, we saw that really PM2.5 is only the one which makes sense to look at, because in terms of data, in terms of quality of translating PM1 and PM10 particle number for, well, several reasons of physical principles. I'm not going to go this is the accuracy is nowhere what we would like to. So we always use only PM2.5, and remembering again that this is not gravimetric, that optical. So also that issue that they don't see smaller particles than 0.3, which is underestimation. So this means that when we use them and analyze the data for fresh combustion emissions or new particle formation, that's where we have the largest numbers of very small particles in ultrafine range or lower ultrafine range. Well, we need to take this into account. So this is the koala. And the abbreviation comes from, it is knowing our ambient local air quality. Why it is like this? We thought when we built it, we thought we should name it, but how to name it so it's not boring? Most monitors at that time had something about air something. So we discussed this once in a group meeting, and one of our master students came up with this abbreviation. And I said, well, if it's something like koala, well, it's local, Australian, and interesting. And that master student came up with this abbreviation. So that's how koala came to be, and that's how koala looks. It's got a solar battery power. Again, I'm not going to talk about this because that by itself will take a lot of time. But these were the monitors which were used in this study, in that paper we are talking about. So koala operation can be operated by a solar panel, that's what you've seen, or a USB cable, outdoor or indoor. Internal battery provides about up to 2 days, actually now even longer. Companion koala, as we call it, is for personal sampling, and we can just attach it to a belt. Real data acquisition at preset intervals, which we can control. Data saved on a build card inside, and also data transmitted to the cloud. And that cloud, where we built up our databases, AWS, Amazon Web Services. So that's how it looks. Data from koala comes to AWS, where it's stored, processed to a part, and then comes to for our processing. So there are some images of building, testing, comparing the koala as the population grew over time and different places, and you can see testing in many different locations. So then what we did, we came with four types of koala in relation to applications. So stationary solar power, like this one, stationary powered from the mains, like this one here, bus vehicle solar powered, and wearable, and that was also equipped with GPS. And then we, over time, this koala population grew, and we did all these studies. So we had 6 networks application in Australia, other like Blue Mountains, that's one there, which we'll talk a little bit later, Brisbane, Gold Coast, Melbourne, Sydney. The first one actually was the Gold Coast for the Commonwealth Games at the Gold Coast. Then there were koala in Perth, Longreach, and Mackay, and 7 networks application overseas in China. That's the Beijing we'll talk about a little bit later. Fiji, New Zealand, Solomon Islands, Sri Lanka, Vietnam. And there are some images from these studies. Each had a different purpose, different application, sometimes very different. So here, this again brings me to the topic of data interpretation and calibration. Data interpretation because of the how they operate, being optical, and that issue of moisture. These are the most important issue. So this is one of our early slides when we were still testing them as well, slides, the demonstration. So what we have here on the top, and the bottom is basically the same but smooth. We have time series from EPA regulatory instrument and from one of the sensors. So if we look at this section here in the circle, which is in the middle of the day, we can see that the sensor underestimates compared to the EPA. Why? Because it's a fresh combustion emissions at the time on that day. On the other hand, if we look at here during night, early in the morning, it overestimates because there are fog droplets. There were fog in the air, and fog droplets are counted as particles. So that we elaborated on this in actually several papers. So this is one aspect of data interpretation. And that issue of humidity is demonstrated here. So in this case, this first top diagram, we have again measurements from a regulatory instrument and a sensor. And there's a situation, no fog, so there's a humidity, but no fog. They then report very similar results. But the lower diagram is there is fog. So it's not just relative humidity, but there is fog. And in this case, during fog, we can see that the sensor, the monitor, significantly overestimate. And there's basically no other way around this, but either drying this or ignoring the data from this period of high humidity or fog. But this very much depends. What is the purpose of the monitoring or data analysis? Now, on the top of this is the issue of different particle sources. And this is because there are different particles, which means different optical properties. And after all, this is optical detection, so optical properties matter. So again, I'm not going to go in details of this, but you can see here for this few slides, Brisbane, Gold Coast, Sydney, and Beijing, you can see the different colors, and different colors here to point of different type of particles: urban background emissions, traffic, fresh traffic, which means smaller particles, black age traffic emissions, larger particles, green marine errors, they will be bigger, orange commercial emissions, which could be a mix of everything. So these different optical types of particle means that we will have then different relationship between what the sensors, what the monitors measure, and what the regulatory instruments measure. As you can see from this graph, different curves and different scatter. Or we can something like this. Detecting one specific problem if we want this, and in this case, spine on a baker. That was the Sydney network. And one of our senior researchers in the group in Brisbane was exchanging notes with our colleague in Sydney, when the network was established, and commented on this. There's something happening around 4 a.m. It is not related to humidity. Humidity is often, and fog is often a problem in the morning, as far as koala data show. All 4 koala shows this, not an instrument problem. John reports from Sydney. Yes, there is a bakery XZ across the road that must start up the oven to cook bread. And Rohan with relief said, oh yes, they must be the culprit. They were a bit late starting up the oven this morning, 4:25. So sometimes it is not really precision or accuracy, but detecting an event, which is important dependently on the application. So over those years and over the many, many projects, I would say it worked. We demonstrated through this project the stability and durability of CO and PM2.5 sensors over several years periods. And we now particularly stress that this is essential quality for them to be used for compliance monitoring. And I come back to this at the end. Then we quote, that's a quote from this paper to which the arrow is, when tested appropriately and used with a full understanding of the capabilities and limitation, low-cost sensors can be unprecedented aid in a wide range of air quality applications, including at that time emerging field of science, citizen science. So these are amazing beasts, but we must know what we do with this, and we must have expertise in this. So in other words, go ahead and use a sensor relevant to your application, to your project. That was our conclusion, and that was our conclusion well, long before this paper about Beijing and Blue Mountains was published, but others were coming to similar conclusions as well. So this was the example of, or is an example of purple air. So each instrument contains 2 plant tower sensors, the same type of sensors we used for koala, available since 2015. As I checked, I haven't checked recently, but at that time, 2021, there were 30,000 reported. And they started being used to support government air monitoring. Now, when it comes to this, of course, the biggest issue is calibration. And for that application for fire and smoke, teams found out how to calibrate it and to reduce the error. Again, I'm not going to talk about the details of this because that could be a topic of a specific presentation. You can see how many papers were published on this. But basically, if you know what you are doing, you can very precisely assess an error. So this brings me now to this paper by Budi and Xiaoting, high PM2.5 concentration during bushfires and haze. So this is based on these 2 networks in Beijing, China, and Blue Mountains in Australia. These are the images of the maps where the sensors were placed next to regulatory instruments. What I have to say at the beginning that the purpose of placing those sensors there was not really in relation to study these events of bushfire, smoke, or haze. There were 2 different reasons. For the Beijing, we worked with colleagues who were at the time studying in generally some aspect of Beijing air quality, but they were also curious about application of low-cost sensors. They were curious because those sensors, local sensors, were less at the time kind of common or appreciated in China. And I'd say it is still the case. And the reason for this is that Chinese networks are so advanced and sensor monitors, which are used for monitoring air quality across Beijing, capital cities, big cities, and everywhere, are much sophisticated than just low-cost monitor. So that was, in a way, a less interest in using this for regulatory purposes, but more curiosity from our colleagues. On the other hand, in Australia, in the Blue Mountains, this was an interest from the New South Wales EPA. There were some issues in that area of Blue Mountains, which is west of Brisbane, about 100 kilometers west of Brisbane, very beautiful area. And some community complaints about some sources. I must say I can't remember now exactly what the issues were. And they wanted to, well, to first have to test how those monitors, how it works, but also to provide some information to the community. So as I said, the purpose was not specifically on this. But when, from retrospection, when Budi and Xiaoting realized the sort of the amount of data, they thought, well, let's look at this specific aspect. So in sort of summary, what the methods of the data analysis, not set in this study, was selecting approximately 30 days for each season as the extreme air pollution periods based on concentration of air pollutants. Now, here the complication comes. Haze events in Beijing differ in their source, formation process, and chemical composition. So there are 3 categories which we investigated. The pure haze events in winter, and this is mainly caused by PM2.5. There's a wealth of understanding data on this. The mixed dust haze event in spring, which is always accompanied by dust storms, that means coarse particles. And then mixed fog haze event in summer, which is accompanied by high relative humidity. Now, so looking at these different types of haze, which has characterized by high concentrations, you can see that there are different sources, different level of humidities. So we cannot expect that what we'll see in terms of the data will be the same for each of these situations. Now, in Blue Mountains, on the other hand, which we have much less of this, we focus on bushfires events, two bushfires event, and that was the winter bushfire event and the summer bushfire event. So at a glance, how did it look like? So time series of PM2.5 and CO concentration for winter haze events. So, and this was for Beijing. Sorry, I didn't write it there. So in general, when you sort of look at a glance and compare the blue and green lines, which are the two sensors, with red, which is regulatory instruments, you can see that the trends in terms of occurrence of peaks are very, very close to each other. However, the heights differ, and now we are not surprised that the heights differ, because it depends what's happening in the air, whether they overestimate or underestimate, dependently of what type of particles is. And this is the situation with bushfire events. So, and again, the same story here, that it is a very good relationship between the monitors and the regulatory instruments, but the heights vary. So now this is even getting more complicated when we look at this, specifically at the scatter plots, and then we'll start with Beijing during haze events. So we have three images here, and each is for different seasons: summer, winter, spring. Now, it is not this is just a different season, but different haze events, which means different types of particles, different types of optical properties, which means different types of optical properties of the particles, and different issues in relation to humidity. So it's not surprising that we see different images. So the dashed line is the line of equality. And what we can see from these graphs, that the deviation is the greatest during summer. And the conclusion is because humidity is the highest, and humidity is the high humidity means a lot of water particles being counted as particles, which means concentrations are higher than the concentrations by regulatory instrument. And in this case, it was BAM. Now, in those other types, as winter and spring, the slopes are similar, as you can see, with the slope 1.54 and 1.58. The slopes are very similar. It is what we can see, the scatter is different. And then the scatter will be different because still, even so, the humidity is perhaps less an issue, but even this, we can see that there are types of humidity marked by this. Still, there are different types of particles, dependently which haze event it is. So this was Beijing, and now in Blue Mountains. In the Blue Mountains, this situation is this. So we had just identified two of these times when bushfires were winter and summer. And what we can see that in case of the winter, so maybe I should say the dashed line is the same as before. The dashed line is the line of equity. So in this case, we have a very different situation. We can see that the deviation is similar, but in the opposite directions. Now, again, because of different processes taking place in addition to bushfires. We also, during that winter, didn't have a lot of bushfires. There were relatively few times, even so during that 30 days of bushfires. Actually, in Blue Mountains, I'll have this as a last slide. There's another very interesting phenomenon, and the reason why they are called Blue Mountains, but I'll keep you in suspension until the last slide. But it has to do with new particle formation. So this will then, and that will be particularly in summer. So without going to sort of more detail into this, because that was not the objective of the paper to interpret all of this, but to show the performance, we can see how much what the reading depends on what type of particles it is. But overall, if you have enough data, particularly like in Beijing case, the line is reasonably good. So what's the future of application of low-cost sensors? 2 years ago, we published this paper, mandating indoor air quality for public buildings, scientific consensus of a large interdisciplinary group, and we call it a blueprint for this process. That's a photo which we discussed this issue of mandating of indoor air quality regulations with our Prime Minister in Canberra 2 years ago. Well, we've proposed in that paper the standards. And you wouldn't be surprised now, looking at the pollutants we recommended to monitor are this PM2.5, CO. These are the two pollutants which are the basis for koala. And this is exactly for the same reason I discussed at the beginning of the presentation. And there's also CO2. Now, CO2 I didn't mention before because CO2 for air pollution measurements outdoors is not really relevant, even so there are interesting things happen there, but it's not relevant. However, CO2 is very important for indoor air, and not that much, and often not that much because of the concentrations, but because being a proxy for infection transmission and ventilation. So we proposed the values based on different air quality guidelines, scenarios. I'm not going to talk about this, but also we've stressed that actual levels adopted by countries and jurisdictions will differ, reflecting local circumstances and competing priorities. So I wouldn't worry sort of analyzing this much and talking about much about specific levels, but what pollutants we recommend to measure. All right, but if we do this, it comes back to low-cost monitors. Now it's the P-block project. This is something where we want to demonstrate that a real building can, in fact, meet this proposed indoor air quality standards and using for this low-cost monitors. So this is the building P-block. Well, it's Acuity, my university campus. Actually, this is where my office is at the top of this. Modern building, 5-star certification by Green Council of Australia, which is good, very good, but still some things must be changed, improved for it to meet the proposed standards. So what we are saying, we will retrofit this building and to comply with the proposed standards, demonstrate the compliance in real time, available on our website at all times, document the process, cost benefits, analyze the implications for operationalizations, and so on. Duration of the project, 3 years, then permanent operation, the university will take over. The project, financed by a philanthropist and our university, this is our vice chancellor here in the front, was launched in December last year. So this is the project framework, and what you see here at the very top is starting with the sensors. Without sensors, low-cost sensors, this would not be possible because we cannot use monitors like we are using for regulatory outdoor monitoring. It must be sensors. So sensor data is then fed to control unit and all of this. So then goes through all this process with eventually control, building management system, AWS, AI model, and platform. Some of this is already on our website, but we add, continuously add as the project develops. So indoor monitoring using low-cost sensors. One of the biggest issue is calibration. Without calibration, as you know, nothing can be done. And here, it's not like calibration, like we have several monitoring stations in outdoor area, and someone goes and does the calibration. Here, we would have hundreds of sensors or monitors in each space. So calibration must be done in a different way. And this is what we proposed last year, it was, with colleagues, application for compliance monitoring, and that was the focus, how to do this calibration, how to automate this so it's not that someone is going around. And we also proposed what to do, how to take optical properties depending on the environment. Because in different, like in that office building, the sources, and I'm talking about PM2.5 specifically, will be different and very basically non-existent in that office building. But if you go to a school, there will be lots and lots of particles, particularly dust. So every environment will have different particles, means different optical properties, and this must be taken into account. So Koala now has well, brothers and sisters. So in addition to our original Koala, Koala is commercialized in China in collaboration with Jinan University in Guangzhou. As I said, there's less interest of this in China. However, Chinese colleagues work with countries, particularly developing countries, where those monitors are very welcome. And then there's a new type of koala, new breed of koala, collaboration with company MOT in New Zealand. This is for Australian and New Zealand market. So just a few comments to finish. In general, both PM2.5 and CO operate in a stable, reliable manner without drift and unaffected, but most environments, calibration is very important to take into account the issue of small particles, moisture, and so on. And what we are stressing, that they can be integrated with regulatory networks to provide and address specific questions. And also, data can be used in the absence of any reference instruments to compare with, and uncertainties can be assessed. I talk less about this, but in certain cases, we don't need such a precision if we are to investigate occurrence of a specific problem. Scientific challenges still to resolve. I'm still stressing the scientific bridge must be developed between particle number concentration monitored by low-cost sensors and particle gravimetric mass concentration to relate to existing health guidelines. Existing WHO guidelines are in particle mass. National standards are in particle mass. Here we are monitoring particle number. So that must be addressed. Because it is unlikely that there will be epidemiologicals anytime soon conducted on the exposure response relation to particle number. So this is one challenge on which we are working. And the other is application of machine learning should be advanced to calibrate low-cost sensors, ideally remotely, and that's what we are doing, and in automated way, and to interpret their readings. And application of low-cost sensors for regulatory compliance monitoring should be developed, and that's what we are doing, and accepted that that's really what we should do. So I'll finish with this image of the Blue Mountains. It's not a photo which I took, that's a photo from a gallery. And why they are blue? I don't know whether you have heard about this. Well, these are eucalyptus trees, which are the main type of trees in Australia in general, but specifically in the Blue Mountains. So they emit oil. Eucalyptus tree emit oil. And droplets of this oil are dispersed in the air. So then the process combination with dust and anything else in the air, water, scatter short wavelength rays of light, which are predominantly blue in color. So that's how they look. They are blue. But now this points out that we interpret any data from the Blue Mountains. We also need to consider formation of these particles from this formed eucalyptus oil particles. Thank you very much for your attention.
Fantastic talk, Dr. Morawska. Thank you so much. So I see 2 questions in the chat, and if anyone wants to turn on their mic and ask questions after we read through these, please feel free. But I'm going to start with Kim Ng. So based on this data, would this be a problem if we use this for haze events in Asia where humidity is usually high? And what is the limit for humidity?
Well, with the limit of humidity, we did lots of investigations trying to address exactly this question. Is there a limit where we are sure there's no particle formation? Because it's not just humidity in the air, it is formation of the particles. So humidity can be high, but still particles don't form. So we tried to analyze whether we can, based on the data, all the data of we can compile, whether we can determine the situation. Okay, this is the humidity. Does it mean that there are particles or not? We were not able to find this. But what we then analyzing all the data, well, many set of data we had, we saw that if humidity, relative humidity is below 75%, in generally, we don't have particle formation. So in general, if we really want to be sure that we don't have particle formation, we recommend using this below 75%. But on the other hand, dependently what is the aim of these investigations, since we have time series, and if we don't want to restrict our data to 75%, and we look at the time series, we can identify when formation of when particles, when fog was. In that one diagram I showed, you can clearly see how high it goes at this specific times when fog occurred. So we can also use, and that's machine learning, we haven't done this, but it's possible to identify this particle fog particles to eliminate from the data. But it really depends what we want to use the data for.
And then second question in the chat is from Tristely Mingin. What BMS baseline do you revert to if the sensors fail? What screening is included in the BMS to determine if the sensors fail, e.g. redundant sensors?
Well, so the process will be such. In that building, which I mentioned, P block, will have about 200 CO sensors. Now, there's another issue. CO sensors have to be in every space, every single space, every office, and every little meeting room, but not. But the question in open spaces, large open spaces, we won't need them every few meters. So that, but overall, we'll have about 200 CO2 sensors. However, we already, based on early assessments, we already found out that we won't need that much of PM2.5 sensors because particles are not, there's really no source of particles in the building. Particles come from outside, and they particularly come from outside when there's bushfire or control burning. That's the biggest air pollution source in Brisbane. But if this happens, then the whole building is affected more or less in the same way. So we don't need to measure it in every space. So there will be significantly fewer PM2.5 sensors. And then in relation to CO sensors, where we stated in the paper, they are to be used only when there's a combustion combustion in the space, or and if outdoor air quality standards, outdoor air quality concentration exceed national standard. That's never in Brisbane. However, at the bottom of this building, there's a food court and parking. And in that parking, some years ago, we already published, just happened that we published about CO2 concentrations in that parking. So we will need CO sensors only there. So in terms of how they will be calibrated, this family of sensors, what we stated is that at the time, so that will be done through machine learning, however we'll call this. At the time when there are no other activities happening or building activities, they will be compared through a network. So to all of them to see, like for example, CO2. During the night, there's no people, there's no variation in CO2. They will be compared. And then if any sensor exceeds, and what we'll say, it will be probably 7%, we are not sure exactly what the value was, that sensor will be identified as potentially faulty, and that sensor would be then checked manually what the problem. So all the other sensors will be considered compliant. However, it is still the issue of absolute calibration, which we need to do. And for this purpose, we will have identified so-called reference sensors. There will be 2, maybe 3 of them for CO2, and those sensors will be periodically calibrated, properly calibrated. The situation with PM2.5 will be a bit different, because for PM2.5, in addition to the sensors in the building, we'll have 1 or 2 sensors outside, because the source is outside. So that calibration, and here we have 2 different sources. So the calibration of, but eventually this will be the same, comparing them when nothing's happening, and comparing against a standard instrument. And the standard instrument, now, bringing a standard instrument to a building is a challenge of itself. And this will not necessarily have to happen. And when we think about the future, when this will be used for, well, hopefully all the buildings, it could be by a proxy monitor. So a smaller monitor, like, say, dust tracker or whatever, can be calibrated against a regulatory monitor and then brought to calibrate the reference. The reference monitor for the project. So that's what we are developing right now.
Great, very thorough answer. Thank you. And maybe before we get to the newer questions in the chat, does anyone have any that they'd just like to say out loud? It's okay if not. Okay. Well, let me know. But Yifeng Shu says, as cooking is a major source for indoor air pollution, what about NO2 sensors? What can be done to improve NO2 sensor performance?
Well, it's not that they don't perform. It is the problem that there is interference of ozone with reading of the instruments. So there have been lots of good studies and important studies using NO2 sensors. But the point is that if you are doing this, if you are using this for research purpose, or for research or for diagnostic, but it is done by an expert team, that's all right, because you have means of understanding the data, and you have means to take in ozone or interference with other pollutants into account. So as I said, there's no problem. That's in nature how they operate. But if we were to use this for regulatory performance, for regular compliance, that would not be possible, because this interference is then much more complicated. Maybe in the future it will be possible, but it would then be required. So if we are talking about NO2, in this case, we would also then need to monitor ozone and to take this into account. So the complexity of this right now would be too big to consider this for the buildings. But if you want to use them for research or for diagnostic, they work very well.
Awesome. And then Veronique Perrault says, is the koala data publicly available to anyone like Purple Air?
Well, Purple and Koala are two different instruments because Koala is the monitor we developed and it uses a plant tower. But Purple Air is the monitoring network run by the company. They also use plant tower. I don't think they make Purple Air. I don't think they make the data available. I don't think so. You get data. Well, you are reading because if you have we bought this. We have these monitors. We use them. We check them. So we have the data from our monitors, but I don't think you can have all the data. But on the other hand, I don't take my word for this. You have to check it.
Okay.
But Koala data from our monitors, it depends for which project. For some of the projects, we made the data available through the papers because they've been all the many papers published, and then with the papers, for some of the papers, we publish data as well.
Okay. And then one more question. In using CO2 low-cost sensors in an enclosed space, have you found problems with increased humidity? If so, how can we account for increased humidity? Thank you.
Humidity in enclosed spaces which we investigated hasn't been really a big problem because we are talking now about mechanically ventilated buildings. That's what our focus has been, and humidity is controlled in these buildings, particularly when talking about the buildings here in Australia. Humidity is a huge issue, so the BMS controls humidity. So humidity never has been a problem. However, if we were to consider environments like schools and even schools in Australia, where there's which are most of them are naturally ventilated, which means windows. If windows are closed, then there is potentially an issue. So we haven't investigated this specific issue of humidity in such classrooms. Can't hear you.
Maybe we have time for one more? Is that okay?
Yeah.
It's 4 o'clock. Okay. Has there been a project that integrates AI with the purple air in indoor environments, or is that currently being tested? Thank you.
Again, purple air is not it's not our instrument, and it's not our so I'm not the best person to answer this question. So purple air have been extensively used for this application for the fire data in the US. I have seen something about indoor environment, but I don't think I've seen something about AI testing. But again, that's not something I can answer.
Yeah. Okay. Thank you very much. I think that's all the questions that I see. Thanks everyone for listening.
If there are any more questions after the webinar or from those who are, please send me the questions. I'll be happy to answer them.
Well, thank you both, Lydia and Erin. That was great. It was a wonderful talk, great questions. So thank you very much.